Hello, everyone. My name is Brennan Hill, University of Wisconsin-Madison. Today, I'm presenting our work on the physical basis of prediction, world model formation in neural organoids via an LLM-generated curriculum. This research sits at the intersection of embodied AI, computational neuroscience, and wetware computing. If you walk away with one thing from this talk, let it be this. We are moving beyond treating biological neural networks as passive tissues. We developed a three-part framework to treat biological neural networks as embodied agents. First, it establishes a curriculum of scalable environments. Second, it utilizes large language models to automate the design of these curricula. And third, it allows us to investigate the actual physical synaptic changes that constitute a learned world model. So let's look at this framework. Everything starts with the environment. We place a biological agent in a closed-loop virtual environment. But how does the dish of cells understand the virtual world? It starts with state feedback. You must encode the state of the virtual world, like the position of a ball or predator, to format the biology that understands. To drive learning, we need feedback signals. We ground our learning mechanism in the free energy principle, where agents try to minimize surprise. Therefore, we encode a reward as predictable, low entropy stimulus, like a constant sine wave. Conversely, punishment is encoded as a chaotic, high entropy white noise signal. This represents surprise or mode failure. The physical interface that bridges the virtual and biological is the multi-electrode array, or MEA. This device allows us to stimulate the organoid with those feedback signals and simultaneously record its electrical activity. To close the loop, we need to read the agent's mind, so to speak. We record neural spikes from specific regions of the organoid and decode those spikes into action commands. For example, spike rate in region A is higher than region B, the agent moves left. B is higher, it moves right. This completes the closed loop. The organoid acts, and the environment updates, and the organoid receives feedback based on the consequences of that action. How does learning actually happen? When the agent receives that predictable reward stimulus, it minimizes the system's entropy. Logically, we hypothesize this induces long-term potentiation, or LTP, strengthening synaptic connections that led to that successful prediction. Conversely, when the agent makes a mistake, it receives unpredictable noise. This high surprise signal disrupts the network, introducing long-term depression, or LTD. This creates a push-pull mechanism. Predictable inputs reinforce a world model, while unpredictable inputs weaken this erroneous associations. This is the physical instantiation of model-based reinforcement learning. One advantage of this system is evaluation, as we can measure the hardware. We can use electrophysiology to measure field excitatory postsynaptic potentials, which lets quantify LTP and LTD directly at the synapse. We can layer this with optical imaging using calcium indicators like GCAMP, and we can track the emergence of stable neural ensembles, literally seeing which neurons light up to the present prediction versus error. Finally, we can perform post-hoc molecular analysis, staining for receptor density to see the structural changes that occurred during training. To test this, we propose a three-stage curriculum. First is conditional avoidance. This is the simplest task. The agent occupies a 1D line and must learn to stay in the safe zone, positions 1 to 5, and avoid the adverse zone, which triggers a high entry punishment. Second, we scale up to predator-prey. This introduces goal-directed behavior. The agent, in purple, must actively navigate to intercept a stationary or moving prey in orange. This requires integrating two sensory streams, where am I, and where's the goal? Finally, Atari games, such as Pong, the dynamic interception task, requires a continuous time wave model. We encode the ball's X position and the Y position via frequency modulation. Organoid must predict this trajectory to intercept the ball. Running these experiments manually is slow and difficult. This is where our meta-learning framework comes in. We start with a central data set that logs every spike, every stimulus in the organoid's physiological history. We feed this history into a prompt engineering module. This context is sent to a large language model. Then the LLM generates the experimental protocol, either as JSON parameters, tuning the reward function, or full Python scripts, is designing a new curriculum step. We pass this generated code through a rigorous safety and syntax checker to ensure we don't damage biological tissue. The valid protocol is executed on the MEA function. The results, did the agent learn? Did the capture rate go up? Are fed back to the dataset. This allows LLM to iteratively optimize the training curriculum, discovering strategies that humans might miss. In conclusion, this work offers a unique platform for studying embodiments. By wedding the free energy principle of web computing and LLM-driven automation, we can stop asking if organoids can learn and start seeing how they physically build their world models.